So looking back, we remember that the quadrantal angles are going to produce values of 1, -1, 0, and undefined for our trig functions. Okay, so those are special angles. What we're going to do at this point in the next section is we're done with sinusoidal graphs, or at least learning about them. And now we're going to do the other 4 trig functions. So we're going to do the 2 reciprocals of secant and cosecant. And then we're going to do our friends, tangent and cotangent, who will not do what they're supposed to do. So when I look at this, the reciprocal simply means that I am going to be doing the flip, or I am going to get an inverted ratio. So one of the things to notice, it's going to be easier to graph cosecant, which is the reciprocal of sine, if you graph sine first. Okay, so if you graph sine first, it will be very easy to graph cosecant. So the first thing I want to notice is, where does sine hit the x-axis? Where does sine have a value of 0? Because where sine has a value of 0, that's where his reciprocal cosecant is going to be undefined. So for cosecant, I am going to have asymptotes. So remember, asymptotes are imaginary lines that guide the graph. So I'm going to have these asymptotes right here. And again, I'm going to I'm going to spend time on cosecant, but we're just going to acknowledge secant because they're just phase shifts of one another. Okay, so I've got this one, and then we'll go in and we'll look at tangent and cotangent. All right, so I've got these right here. And then I've got this one. So all these are asymptotes. They are imaginary lines that guide your graph. So notice that wherever sine is 0, cosecant will be undefined. So there's an asymptote there. Okay. Now the fun part is, wherever sine has a peak, cosecant has a valley. Wherever sine has a valley, cosecant has a peak. And so you end up coming down looking like this, because it's like a mirror image. It's a reciprocal, okay? You end up looking like this, and then I can look like this. So he'll go like this. I'm just going to keep saying like this over and over and over again, okay? And I can keep doing that, or, oh my goodness, I can flip the page, and notice I already did it for you. So if you'll notice, the little dotted line right here is the sine function. So you can tell it's sine because that's 0, 0. That's the origin. So what you're looking for properties of cosecant is he's going to be the opposite of sine. He's not going to start at 0 and go up. He's going to start at the axis and drop down. But it's not cosine. Okay, it's the reciprocal. So the cosine would start here and drop down and be continuous. So these valleys and these peaks, or mountains, whatever you want to call them. Okay, if they've got this U shape and this N shape, you're looking at either secant or cosecant. So I know that the opposite of sine, or the reciprocal of sine, starting at 0 and going up, is going to be this thing starting at positive infinity and coming down. These little U shapes keep going up for all eternity. Okay, so as my angle measure approaches 0, okay, this tail is going to go up to positive infinity. Okay, so where's the tail going to go? The closer you get to 0, it's going to go up to positive infinity. What about if I come at 0 from the negative side? Okay, as I come at 0 from the negative side, where's cosecant's tail going? It's going down to negative infinity. So we're going to identify secant and cosecant by looking at where they start. So again, let's look at, now that we've kind of sort of looked at, oh, hang on, back up the truck. We've got to look at asymptotes. So where are these asymptotes? So I'm going to look, I've got asymptotes at 0. I've got one at 1 pi. Okay. I've got one at 2 pi. I got one at negative pi. I got one at negative 2 pi. So I have asymptotes at integer multiples of pi. I have asymptotes at integer multiples of pi. So I want to show you, just remind you about set notation. I could say that my domain is all real numbers. Okay, that's the funny symbol for all real numbers. but not where the asymptotes are. Okay, not where the asymptotes are. So I'm going to use set notation, which is a curly bracket, and you tell me what your domain is. Guess what your domain is? It's X. Okay, then you'll have a vertical bar, and you tell me a description after that vertical bar. So this vertical bar is read as such that. Okay, so my domain is all the x's, such that x cannot be an integer multiple of pi, where k is an integer. Okay, so those are your counting numbers, positive and negative. So like -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are your integers. So your domain is all the x's except x cannot be an integer multiple of pi. X can't be -3 pi, -2 pi, -1 pi, 0 pi, 2 pi, 3 pi, 4 pi. Okay, so that's what set notation looks like. Okay, so you read this as a such that. So what's your domain? Your domain is everything except for where there's asymptotes. Now, what's your range? Okay, so what's the lowest that this thing is going to be? Well, I'm going to have values in negative infinity, and I'm going to come and I'm going to top out at -1. So I'm going to go from negative infinity to -1, and there's a point there, so I can use a hard bracket. Okay, negative infinity, or the infinities always get soft brackets or parentheses, because you cannot equal infinity. It's a concept, it's not a number. Okay, so I've got all these y values coming up till I hit -1. And then I got blank space. And then I'm going to pick back up at +1. So I'll have x values beginning again, or sorry, y values beginning again at +1 and going to positive infinity. So that is interval notation, or you can say y needs to be less than or equal to -1. And y needs to be greater than or equal to +1. So that's just using inequalities. So now we know how to graph secant, which means we also know how to graph cosecant because it's just a phase shift. But let's talk about its domain and range real quick. So this is going to be the cosine curve. That's the dotted part that you see. These vertical dotted lines are the asymptotes. So I need to know where my asymptotes are. My domain, again, is all real numbers except where there's an asymptote. Okay, so where are my asymptotes? This asymptote is at -pi/2. This is -2 pi/2, which is -pi. This is -3 pi/2. This is -4 pi/2, which is -2 pi's. Okay, this is -5 pi/2. So we have -5 pi/2. So I don't know if you see a pattern yet. This is 0. This is going to be a positive pi/2, 2 pi/2, 3 pi/2, 4 pi/2, 5 pi/2. So what's the same the whole time? You've got over 2's the whole way through. So what you're going to have is odd integer multiples of pi/2. So what's the same? Pi/2. What changes? -5, -3, -1, 1, 3, 5, and so on. So your domain for the secant function is going to be all the x's such that x cannot be an integer multiple of pi/2. It cannot be an integer multiple of pi/2, but remember, an odd integer multiple. So that's going to be multiple choice. So odd integer multiple. Okay. Oops, sorry, curly bracket. Curly bracket. All right. So that's how we're going to identify the domains. Another thing to realize, these are not waves. Okay. So the sine function and the cosine function are just used as reference. But the actual graph of secant and cosecant and tangent and cotangent are not waves. Therefore, they do not have amplitudes. You can stretch them. You can make this gap between them wider because it's going to have the same effect. So if I do 5 times the sine, instead of this hitting at 1, 0, well, it's a reciprocal, not 1, 0. Instead of that hitting at 1, it's going to hit way up here at 5. And instead of hitting at -1, it's going to hit way down here at -5 because that affects the amplitude of the sine function. Well, those have to spread out along with the sine function, okay? So there is no amplitude. So if it asks you for an amplitude, there's not one because they are not waves, okay? Their periods are still 2 pi. And then we can look at if it moves up or down, but we're not going to look at phase shifts until 7/8. Okay, so now we want to look at tangent and cotangent. And remember, they're just kind of sort of off on their own, being weird. So when I graph tangent and cotangent, tangent and cotangent are kind of sort of going to look a little bit like x to the third. They are not x to the third. Okay, this one is not x to the third that's been flipped. They just have that similar shape, but they are not equivalent. Remember that tangent is the same thing as sine over cosine. So whatever sine does, tangent is going to have the effect. Okay. In other words, sine goes through the origin, so does tangent. Okay. Sine goes through the origin, so does tangent. Sine moves up and to the right, so does tangent. Okay, but where are my, first of all, what's the period of my function? The period of my function is pi, and the period of my function is pi. So when we look at page 1, if you're asked about a period or if you're asked about a phase shift, they both incorporate omega or b. Okay, in this case, the period is going to be 1 pi over your coefficient of x. Okay, and it's not going to matter here, because you're not dealing with period. All right, so all you have to do is remember that instead of dividing it into 2 pi, the period is supposed to be 1 pi. So you'll take that just for tangent and cotangent. So when I graph these, I'm looking at this, and then I want to look at where the asymptotes are again. So since this is at 0, this is going to be about, this is going to be at negative pi over 2, and this is going to be at positive pi over 2. So one of the cool little benchmarks that you can look at is the fact that the halfway point between the asymptotes, so in this case, if this is positive pi over 2, which is half of a pi, and if this is negative pi over 2, which is negative half of a pi, the halfway points would be pi over 4 and negative pi over 4. By definition, the tangent of pi over 4 is 1. So the halfway point between this center point of symmetry and the asymptote should hit at 1 unless you stretch it. Okay, so the period may be affected. It may have a phase shift, but look at the width of the period, find the halfway point, go up 1 and go down 1, or unless it's been stretched. So if you've got a factor of 5 here in front of your function, then instead of this being at 1, it's going to be way up at 5 and down at negative 5. Okay, so cotangent is going to be the, I already told you, by the way, how to represent those asymptotes. So they'll be at negative pi over 2, positive pi over 2, 3 pi over 2, so they're integer odd multiples of pi over 2. So look at cotangent. Cotangent is the same thing. Cotangent theta is the same thing as cosine theta over sine theta. So whatever cosine does, okay, it's going to have a similar effect on cotangent. So since cosine starts up here at 1 and drops down, okay, cotangent's going to start up here, good heavens, and drop down. Okay, start up here and drop down. So it's not going to start at the origin. And I just gave you this dotted line representing tangent just as a point of reference, so you can kind of see what's going on. So you'll notice they're really symmetric. They're kind of pretty. All right, so what do I know? Cotangent is also going to have a period of pi. Cotangent is going to do integer multiples. Its period will be in integer multiples of pi. So this is a width of pi, this is a width of pi, this is a width of pi. And it goes on. And I recognize that it kind of sort of follows along with what cosine does, and that it starts at a high spot and drops down to the right unless I flip it or something like that. So those are our basics on how to graph these things. And what you'll do is you're just going to have to use multiple choice on this section. You don't have to graph them like what we did in the last section where you have to choose sine or cosine or whatever. So you'll just choose multiple choice and go from there. So it's a pretty straightforward section, so I'm going to leave it at that unless I get a flood of requests for some examples. So there you go.